Our objectives for section 2.2 are: identify intervals on which a function increases, decreases, or is constant. Use graphs to locate relative maxima or minima. Test for symmetry. Identify even or odd functions and recognize their symmetry. Understand and use piecewise functions. Find and simplify a function's difference quotient. Okay? Now the thing about this section is that in high school, a lot of this is taught in pre-calculus. Okay, so some of this you've seen before. We've talked about increasing and decreasing. We've talked about symmetry. When we talked about quadratics, we talked about maximum or minimum. So like the vertex, whether it was high or low, opening up or opening down, those kind of things. But the other things, even or odd functions, piecewise functions, and difference quotient, that's all in pre-calculus. So those are all new things today. Okay. So let's start by talking about increasing, decreasing, or constant. I'm going to show you this graph that's in the textbook because it's pretty interesting. Average fuel efficiency of the new U.S. passenger cars. So it goes to 2014. So new as in 2014. How about that? Okay. It's just talking about new cars in general, and the graph only goes from 1955 to 2014. Okay. So it's saying, if we're talking about increasing or decreasing, what intervals is this decreasing on? Do you see anywhere that it's decreasing? Yeah, in the beginning it's decreasing, isn't it? This is lower. This point is lower than that one. This point's lower than that one. This point's lower than that one. So as x's are increasing, the y values are decreasing. Now, not a whole heck of a lot, but enough that you can tell by looking, right? Even when they're talking about 15 miles per gallon or 16 miles per hour gallon or 20 miles per gallon, something like that. It's decreasing there in the beginning. Is it increasing anywhere? Everywhere else, right? From here on, it's increasing. Now, this is a steeper increase than, say, this distance right here, this domain, but it's still increasing nonetheless, isn't it? What? Yeah, Prius. Yeah, 1975. That's when the Prius came out? No, I was making that up. I was just saying. Okay, but all these others are increasing. Now the other thing that it says is increasing, decreasing, or is constant. Okay? Is anywhere on this graph constant? It doesn't look like it to me either. We would have to have exactly what the data is because that's pretty close. But it even says it's decreasing, like in the words that they gave us on the graph. It even says it's decreasing. Okay, so constant means it's going to be perfectly exactly horizontal. Okay, that's what they mean by constant. Okay, so let me show you a couple more graphs. Down here, well, you don't care if it's down at the bottom or not. I'm just saying here's a graph. This function is increasing because as we're going from left to right, as x's are increasing, so are the y values. Okay, now the interval, it's saying what interval is it increasing? It's just asking for its domain. What domain values is it increasing over? Well, it's increasing from this open circle to this open circle. So if we had the points of those, we could write an interval notation or an inequality notation of the domain over what it's increasing. But you know it's increasing when f of x sub 1 is less than f of x sub 2. This value is less than this value. Does that make sense? Whenever x is less than x sub 2. So if this value is less than this value is less than that value in the interval. That means it's increasing. So decreasing, does it make sense that they would be the other way? This one is less than this one, so f of x sub 1 is higher than x sub 2, and x sub 1 is higher than or lower than x sub 2. Okay, so both of these, the x values are the same. X sub 1 and x sub 2. X sub 1 has to be less than x sub 2. X sub 1 is less than x sub 2. It depends on the y value, which one is higher, which one is further up on the graph. Is x sub 2 higher? If it is, then that means it's increasing. If x sub 1 is higher, that means it's decreasing. Okay, and then last is the constant. It's constant if x sub 1 f of x sub 1 and f of x sub 2 are the same. See if they're equal for the interval from x sub 1 to x sub 2. Does that help? Okay. So if we're looking at a graph like this, we know this is a cubic because if it's got x squared and x to the third, and we call it by the highest exponent, right? This is a cubic. So on which intervals is it increasing? Well, can you tell that it's increasing from here to here? Okay, this is increasing. Once you get here, it's not increasing anymore. It starts to decrease again. Okay, it's also decreasing here. Now, some people have a little issue with that because it looks like we start here and go that way because there's an arrow up there, right? Well, so that looks like it should be increasing. Except when we're reading intervals like this, when we're trying to decide if it were increasing or decreasing, we go from left to right. So left to right, that's decreasing, that's increasing, that's decreasing. That makes sense? And then this one is constant, and then starting again here, it's increasing. Now that looks like a weird function. That's not any sort of function that we looked at in Algebra 2. That's called a piecewise function, which is something that we talk about later in this exact section. Okay, piecewise functions. But how are you feeling about increasing and decreasing? On a parabola, sometimes they talk about the vertex being the only place where it's not increasing or decreasing. So if you're talking about, let's pretend this is a parabola right here. It's not, but we'll pretend for a second, okay? It's decreasing from here to here, not including 0, because 0 is just, that's like its turning point. And then it's increasing from 0, not including 0, all the way to 2, not including 2, because 2 is where it changes direction. No, not really. I don't think so. It's just that, yeah, it's just a turning point. It's just where it changes direction. Okay? So, you're feeling okay on increasing, decreasing, or constant? Okay. The next thing is using graphs to locate relative maxima or minima. That seems pretty straightforward. Okay? If I'm looking at a graph to find its relative minimum or maximum, that's a relative maximum. Now, does it ever get higher than that? Well, yeah, it sure does. It has an arrow going that way. But in this small area, can you tell that that's the highest point? In this small area, can you tell that that's its lowest point? Now, it goes lower than that. You know that because the arrow goes on down. But relative minimum or maximum is saying if it's changing directions, where is that change of direction? That's going to be a relative something. If it's decreasing and then increasing, that's going to be a relative minimum. If it's increasing and then decreasing, that's going to be a relative maximum. So almost you're looking like for a vertex. If we were talking about a parabola, you'd be looking for a vertex, right? Other functions that look like this, we're not looking for a vertex so much as we're looking for a change of direction. Thank you. Does that make sense? Okay. Is there an informal way to think about relative maximum and relative minimum? You may find it helpful to relate the definitions to the graph's peaks and valleys. A relative maximum is the value at its peak. A relative minimum is the value in a valley. I just thought that was interesting. Okay. If you're having trouble thinking of this in math terms, think of it in geography terms, I guess. Okay. Okay. Let me make sure. Yeah, that's good. How are you feeling on maximum or minimums by looking at the graph? Could you find them? Okay, test for symmetry. That's next, is test for symmetry. You have to be able to look at a graph and tell me the symmetry. All right? Now, this is interesting, this little figure to the side. It says, to most people, an attractive face is one in which each half is almost a perfect image of the other half. Now, I know it looks kind of creepy up there on the screen just because of all the lines and everything. If you look in the actual book, it's portraying what it's saying in the sentence. Does that make sense? Look at right here. See? It's portraying what it's saying on the sentence. The screen distorts it a little bit. I don't mean it to look like that, okay, but I can't do anything about it right now. You know what I'm saying though, right? Okay. Yeah, it's not a shine. It's the fact that I have the screen at a different scale thing than the actual image itself. Does that make sense? Because like my hand looks like really short and choppy, and in fact it's a beautiful hand. Okay, all right. Anyways, look at these graphs. Okay, could you look at this graph right here and tell that it's symmetric to the y-axis? How would you tell that? Besides the fact that it says right here. If you chopped it in half down the y-axis and folded it up on itself, would it be right on top of each other? Yeah, so there's a symmetry there. Okay? Can you tell this one is symmetric with the x-axis? Because if I chopped it in half right there and folded it up on itself, would it be right on top of each other? So that's symmetric to the x-axis. Okay? This would be symmetric to, it says the origin, right? This is a rational function, or at least it looks like a rational function to me. And when we talked about rational functions, we also said it also has a line of symmetry at y equals x, didn't we? Because if we folded it up this way, it'll be right on top of itself, won't it? Okay, but the important thing they want you to know here is that we call this symmetric to the origin. Okay, any questions about that? So there's definitions of symmetry. There's a chart in your textbook called definitions and tests for symmetry. The graph of an equation is symmetric to the y-axis if for every point xy there's a point negative xy that's also on the graph. Okay, so if it's symmetric to the y-axis, the x changes signs. So guess what happens if it's symmetric to the x-axis? The y changes signs. Okay, and then so if it's symmetric to the origin, both of them. X is negative x, y is negative y. Okay, we'll finish the rest tomorrow. Okay, have a great day.